Buenos días a todos. Como presidenta del grupo especializado de cristalografía y crecimiento cristalino, quería daros la bienvenida a esta última conferencia de la serie Ciencia en la Red que hemos venido desarrollando a lo largo de estos últimos meses con un gran éxito. Este éxito se debe sin duda a la gran categoría de los conferenciantes que hemos tenido y a los cuales hemos tenido y tenemos hoy, a los cuales quiero agradecer de nuevo su amabilidad. Pero también sin duda este éxito se debe a todos los participantes que habéis asistido a las distintas conferencias. Sin duda, como ya he señalado, el de hoy va a ser también un seminario muy interesante, por lo que no quiero utilizar más tiempo. Solamente quería animaros, aquellos que no seáis del grupo de cristalografía, haceros socios del grupo. Ya sabéis que se puede hacer socio a través de la Real Sociedad de Física o a través de la Real Sociedad de Química. Esta serie de conferencias la reanudaremos cuando empiece el próximo curso en septiembre y la programación la haremos pública próximamente. Nada más, simplemente desearos a todos un buen descanso, unas buenas vacaciones y os dejo con Guillermo Mínguez, que hará la presentación de nuestro conferenciante de hoy, Josep Puigmartí-Luis. Muchas gracias a todos por vuestra asistencia y por supuesto al conferenciante por acompañarnos hoy. Nada más.
Gracias, Pilar. So, dear all, welcome to our last seminar of this season, organized by the specialized group on crystallography and crystal growth of the Spanish Royal Society of Chemistry. For those of you who don't know me, I am Guillermo Mínguez, Associate Professor at the University of Valencia, and I will be chairing today's talk. So the talk today, we have what promises to be a fantastic talk on controlling self-assembling processes by using microfluidics. It will be given by Josep Puigmartí-Luis, who is an ICREA professor at the University of Barcelona, which he joined over a year ago from ETH Zurich. Before leaving you with the talk, let me just remind you that if you have any questions, please use the chat and we will address the question to Josep at the end of the talk. Please indicate the name and the affiliation so we can address properly each of the questions. And now, Josep, please let us show us.
Thank you very much, Guillermo, and also al Grupo Especializado de Cristalografía y Crecimiento Cristalino for giving me the opportunity to present our work. So as you mentioned in your nice introduction, so the idea of today's presentation is to show you how we started to try to control crystallization processes. So what is clear is that we are surrounded by turbulent flows, right? So the wind is turbulence, also the surface currents in oceans, seas, they are all turbulent. But it's very important to control the fluid streams across scales. And let me give you an example of that. So in order to control biomolecular interactions, it's very important to control the fluid streams. And that's the example I want to show here today. So what you see here, these pink dots, these are calcium atoms. So the calcium atoms can interact with the troponin, this protein here. So this interaction, what it does is that this helical protein here, the tropomyosin, can contract, and by doing so, then the actin, as you can see here, it's showing up. So this controlled diffusion of calcium enabled us to reach this state where you have the actin visible for the myosin to bind to it. So, and how do we break that? This can be broken when ATP molecules will interact with the myosin. So then they generate the ATP, and this bond then can break. So because of this controlled diffusion of calcium and ATP molecules, it's possible, I mean, we can move out of our muscles. So this is, as I said, due to a controlled diffusion, as you can imagine, in confined spaces. But what do we do in the lab? In the lab, what we try to force is that the fluid streams, mix as fast as possible. And for doing this, we create turbulent flows. So by no way or by no means we are in such conditions like the ones shown here. So the question is, how can we achieve this control in the fluid flows? So, well, if we look at fluid mechanics, I will not go so much into details here, but there is an equation that it's filled with partial differential equations, and this equation, it describes how the motion of fluids happens. But most importantly, out of this equation, it's possible to extract dimensionless numbers that they define the behavior of fluids. So they describe how fluids will behave. And among these numbers that you can see here, there is the list is still longer than that. I would like to focus in this first section of my presentation about talking about the Reynolds number. As you see that there, this dimensionless number is the ratio between the inertial forces and the viscous forces. So the question is, what will happen if we have a very low Reynolds number? So in the same way, we can have the same question, what will happen if we have a high viscosity, a media or an environment with a high viscosity? What will happen to the fluid flows on these conditions? Well, here we have the example, right? This is a container, is a viscous fluid, so the viscosity is very high. So we have, the Reynolds number in this container, it's very low. And this is what happens when you try to mix this, for example, these three different dyes. So what you see there, we start to turn. So they look to, that they are kind of mixing, but when we go backwards, you see that we reach the initial state. So what this shows us is that at very high viscosities, we can control with high precision how much we want this, in this case, in these dyes to diffuse towards the others. When I present this video, I always have some complaints. I mean, if there are mechanical engineers in the audience, will not question that. But if you have like a chemist or a material scientist, they tend to question this because it's not what you would expect. And this is why then I also added this video here. So what you can see is that we have the same, container with a very high viscosity. We do the square, and when we go backwards, we reach the initial state. So what this clearly showing us is that under these low Reynolds number conditions, we can have control over the diffusion of regions. But the question here is, what can we do with that, and how we can achieve, these conditions in conventional laboratories? And this is exactly what we try to do. I mean, there are different ways of doing this, but in our group, we focus on using microfluidics. So now these are water streams, but because of the small dimensions, what it happens under these conditions in microfluidic devices is that the viscosity is really high. So at the end, we will also have low Reynolds number. And what you see here, these are two dyes that are dissolved in water. But what you can see is that these two dyes do not mix even in, the channel is 1 centimeter long. We will reach the end, and you will see that these dyes didn't mix through the entire channel. So, and this is so-called laminar flow condition. So this happens because we have this low Reynolds number. But more interestingly here is that now this happened because we had really flow rates here. But when we decrease the flow rates, what we can do is we can decide how much we want this dye to diffuse towards this aqueous stream here. So what you see now is that all along the main microfluidic channel, that it's around 250 micrometers, we can manage controlling the flow rates so that the dye will diffuse completely towards the other side of the microfluidic device. So, and this is very important because what this tells us is that with microfluidic devices, we can control the diffusion of regions in time, but also in a space. So we are trying to meet this condition that I showed at the beginning when we were, I was explaining the mass contraction. So, okay, so right now we have a technology that we can use in the lab in order to achieve these reaction diffusion conditions. So, but the question is, what can we do with that? So, and most importantly, we have to also question, so what is the approach that frequently chemists and material scientists are using in the lab to achieve, new functional materials? So, and this is, summarized in this slide here. So what we normally use is turbulent mixing. So what we want is that the reagents mix as fast as possible. We also have magnetic plies that we can put here in order to enhance the mixing. But I put in this video here because what you can see is that, the concentration of the reagent is not homogeneous all around the reaction vessel. So that's something that we cannot easily control with doing conventional synthesis. And then let's suppose that we want to have a 2D material with our, synthetic protocol. So the first thing we will do is we will design molecules that we think they will assemble in the way we want to achieve the 2D material. And then if this does not happen, we will start to change parameters like time, temperature, pressure, solvent composition, and if this does not work, then what we will do is we will change the monomers and we will redesign them in order to achieve our expected goal. And here, playing with these conditions, what we normally achieve is the most thermodynamic stable product. We isolate the product that is more thermodynamically stable. So the questions that we wanted to answer when we started to work with microfluidics were the ones listed here. So what is the effect that these reaction diffusion conditions can do to the self-assembly processes? Can we, by using these conditions, also achieve, different pathways in a given energy landscape? Can we generate gradients? Well, you saw that this is possible, but why are they useful? Why we need to generate gradients? If you talk to a biologist, they will tell you that chemical gradients are very, very important for every sophisticated function that occurs in the human body, right? But for materials, for material synthesis or for crystallization, why are they important? So then can we also control the nucleation of crystals? Can we isolate them? And further, can we control the shape of crystals? Can we control morphogenesis? These are all questions that we initially had when starting working with microfluidics. So, during my PhD, I was working with this molecule here, that tetrahydrofuranol. So I'm an organic chemist, by the way. So what I used to do, it was to derivatize the TTF, with different functional groups in these positions, because as you know, the TTF is very well known in the field of molecular electronics. So what you want to have is an organization where you have a very good pi-pi stacking of this molecule, so that when you oxidize or partially oxidize the structure, you will achieve, you know, the formation of a conductive material. So here I'm just, you know, showing some results that they were developed in the group of Professor David Amabilino. So I did the thesis with Professor David Amabilino. And this is a paper they published some years ago, where they show that when you have a very long alkyl chain, what you see, this is the STM image. So what you see here brighter is the part of the molecule that has the higher electron density. So this means this right part here, this is the core of the TTF. So what you see in this case with these functional groups in these positions is that the molecule is lying flat on the surface. But what I told you is that for having a conductive material, what it will be more interesting is to have an organization like that, where you have a very good pi-pi stacking of the molecule so that it organizes perpendicular to the surface. So as I said, I was playing, you know, with the functional groups, and we managed to achieve different structures that could, as you see in these STM images, you know, organize as we wanted them to organize on the surface. So this is very nice. But the question here was, when I was doing all this work, is like, do we really need always to change the functional groups, you know, to control self-assembly? So that is where I started to think about technologies that will allow us to control self-assembly without the need of doing purely organic chemistry. So, and this is actually the first paper, obviously. I mean, I was working with TTF. So the first paper I published with working with microfluidics is this one here. Obviously, I work with the TTF, but look at this now. So we are using the bare TTF, so we don't have any functional groups there. And what we do is this oxidation reaction. So the TTF oxidizes, we reduce the gold salt. And what we have is the formation of this charge transfer salt. So it's very important, and I want you to pay attention here, because this is a terminology that will appear later on the presentation, and it's about the flow rate ratio. So I define the flow rate ratio as the ratio of the seed flows versus the reagent flows. So what you see in this condition here is that the flow rates of these two reagents, it's very high, higher than the seed flows. This is why you have a very low flow rate ratio. But when you have very high seed flows, then what happens is that you confine the reaction area. So as you can see, playing with the flow rate ratio, you can define the time that you want these two reagents to react, but also the space where you allow them to react, right? So what we observe is that when we work at very low flow rate ratios, what we have is a mixture of crystals. So they don't have a defined morphology. But as soon as we increase the flow rate ratio, what we observe is that we can even, you know, change the crystal habit and obtain nanowires. But most importantly in this work, it was to prove that, you know, by changing the flow rate ratio, we were able to change the pi-pi stacking distance of the product. And this is very important, not because we did it, but I think this clearly proves that, you know, if you remember what I showed before, I always had to change the functional groups in this position in order to control, you know, the stacking of the TTF molecule. And here what we prove is that only changing how they mix, so the fluid streams, how they behave, we are able to change the pi-pi stacking distance of the final product. And of course, also the morphology. So our next study, it was, you know, to what we wanted to do, it was to accelerate reactions. This was already published by the group of Professor Daniel Maspot. So they published this in JAX, I think it was in 2010. So they did this coordination polymer, and it took them some days to generate the nanofibers. So the idea here was to see if with microfluidics, we could accelerate the crystallization process. Well, this is what you can see here. This is again a 4-inlet microfluidic device. So at the interface of the two regions, you see the formation of this bundle of nanowires. So we can generate the crystals in 300 milliseconds. So we don't need days in order to get these coordination polymers. And then with the microfluidic device, if we change now, if we have all the flows, the flow rates, if they are equal, so we have a perfect, generation of the bundle until the end of the microfluidic device. You can also see it here. So as you see, some people ask me, why is it that you have a wider bundle here? So the answer, I already gave it before. It's because we are enabling that these two regions diffuse more and more and more downstream. So this is why here we have, a thicker bundle of nanowires. But also note this here. So if we change the flow rate in these positions, we can also guide, the coordination pathway of this coordination polymer. But then, of course, if we alternate the flows, what we have is also the parallelization. So we can have a parallelized synthesis of this coordination polymer. So that was very, we were quite surprised that we could generate these bundles of nanowires in 300 milliseconds. But the question was then, can this, the shear stress that these, fibers that are generating, can this also help to arrange other coordination polymers in fibers? So, and this is actually what we were searching in collaboration with the group of Professor Daniel Maspok. We were looking for a coordination polymer that will not generate nanofibers. So in this case, what we observe is that this silver cysteine, it generates, this coordination polymer, it generates like a kind of membrane. And with time, you have the formation of these microcrystalline particles. So the idea is, okay, this is a good candidate. Then let's see if we can generate some other type of morphology when we do the synthesis with microfluidics. And this is what we did. We have the 4-unit device. So we have the cysteine, the silver. And what we observe is that now, because of these controlled reaction diffusion conditions and the shear stress that this coordination polymer experiences when is being generated, we can observe the generation of fibers. So instead of membranes, what we observe is the formation of fibers. And we also observe the formation of silver sulfide. This is a semiconductor crystal that it's generated just because of the morphology. I mean, you cannot generate this in the membrane, but when you have fibers, when you focus with the E-beam on those fibers, you can generate this semiconductor out of a biotemplated, functional material. So the idea then it was like, okay, so we have shown that we can, accelerate the formation of coordination polymers. We can change the morphology. Look what I'm saying. We can change the morphology. I'm not saying that we can control the morphology. This is something that will come later on in my presentation. Here, we only change from a membrane-like structure to a fiber-like structure. But then the idea here was like, and this is done in collaboration with Professor Felix Zamora at the Autonomous University of Madrid. So the idea here, it was like, can we also, accelerate the generation of covalent organic frameworks? Because as you know, covalent organic frameworks, they need some time to, synthesize. And we wanted to see if we could, the same way we did with the coordination polymers, so if we could also accelerate the synthesis by using microfluidics. This work, happened also because a good friend of mine, Professor Ruben Mas, we met in, in a Biennale, in a conference, and he started to, to talk about this possibility, this experiment here as well. And what you can see is that when you do the bulk synthesis of this coordination, of this covalent organic framework, so what you have here is the 3-aminophenylbenzene, and then this is the the benzene carbohaldehyde. So when you do the reaction of these two, you have the formation of the COF. And if you do that in bulk, what you see is the formation of this, powder that has not a defined morphology. So when you do the synthesis, with these flow rates in our microfluidic device, what you observe is the formation, like, the material now has a more defined morphology. It's like a fiber-like morphology. And look at this here. So this is the synthesis in bulk, and this is what we obtain with microfluidics. So this synthesis is again done at 300 microseconds. So after 300 microseconds, what you can see here is that the diffraction peaks are much clearer in our product than the one that you obtain in bulk. And most importantly, I will show the video afterwards. What we can do is we can process the COF now. So, COFs are very difficult to process because they are very difficult to dissolve, and therefore it's very difficult to print them. So here what we could do, and this was highlighted in chemistry world, it was to 3D print the COF in arrays and also writing different words on different surfaces. So let me show you the video. I mean, this is the outlet of the microfluidic device, and what you observe here is the COF fiber that we are generating via this microfluidic approach. So this was, we were very happy with this, these results. And then I would like to jump to a second example, and this is more related to, to the idea of isolating intermediate states during the crystallization process. So we have shown that we can, with microfluidics, we can control reactions in time and space. So the question then that rises is like, can we isolate intermediate states that are being generated during the crystallization process? Well, with this coordination polymer, this copper butyridine, so if you do the reaction in bulk, what you have is the formation of these square planar crystals. So if we do it, with really low seed flows, so with a really high flow rate ratio, what we observe in the microfluidic product is the same thing we have in bulk. But as soon as we start to increase the flow rate ratio, what we realize is that now we are achieving a series of unprecedented structures that we cannot obtain in bulk synthesis even when we add surfactants. So it's not possible to achieve these structures. We can only achieve them when we do the microfluidic synthesis. And this is what we observe also. The diffraction pattern of all these structures are the same. So what we have here is a clear case where we are isolating, we are freezing the crystallization process towards this most stable thermodynamic form in this coordination polymer. And this is something that I've been working lately, and I think I don't need to explain this here, but there are two communities that that believe that crystallization processes can go different ways, right? So there is the classical nucleation theory, where you have your ions molecules that they assemble monomer by monomer to achieve the thermodynamic product. But then there are other researchers that, like for instance, one of the professors very active in this field is Professor Helmut Holfen at the University of Constance, and they believe in this mesoscale assembly. So what they say is that it's not always like that you go through a monomer by monomer assembly, but it can happen that you can generate other structures that then will organize and generate the final crystal structure. And I still believe that these stages here can lead you to a different product. And this is something that we are currently working in the group. So I think that if we are able to control this mesoscale assembly, this metastable state, it will be possible achieve materials with new functionalities. But let me give you an example of that. So this is work that we did together with Professor Guillermo Mínguez here present. So I remember that I visited him some years ago, and he showed me this this compound here, and I was very excited about this habit, the crystal habit. And I remember that I asked him, hey, and do you know how these things grow? And he told me, well, we never look at it. And then I told him, let's see. I mean, the next thing he said is, we do that in acetonitrile. And then I said, perfect, because this is a solvent that we can use with our microfluidic devices, because normally they are made of polyvinyl siloxane, even though now we use also glass chips. But the idea there it was to do the same as I shown before, to see if we could, like freeze the crystallization process of this crystal here. So we, in that case, we fixed the flow rate ratio to 1. So we have the same flow rate in all the inlets. So in one inlet we have the iron, and the other we have this the tetrazole derivative, and then here we have acetonitrile. So what we observe is that from 1 to 6 hours, these hexagons grow, as you can see here, from the vertices. Whereas from 6 hours to 12 hours, it seems that now the crystals, they are growing not from the vertices like here, but from the faces. So this was something that surprised us. And what we observed also, it was that, after 24 hours, we had this perfect hexagonal shape of the crystals. So what this clearly tells us is that, in fact, what we are observing, it's 2 different pathways of crystallization for the same product. At the end, as I said, we obtain always the most thermodynamic stable form. So we started, and this was done by Guillermo in Valencia. So we started to, think what was the effect. I mean, why the vertex growth will be first. And he was looking at the crystal structure, and what we realized is that, it seems that if the growth will go this way, we will have more ionic interactions. Whereas in this case, from the faces, this will be mainly triggered by van der Waals interactions. So this is why we then thought that it's reasonable that the first growth will be from the vertices and later on from the faces. So we submitted this publication, but no one believed us. So they didn't believe that that was the case, and they even doubt that this was real. I mean, you can clearly see that the growth is different here, because you have a shift of 30 degrees there, whereas here is just parallel, right? So what we decided it was to do full atom molecular dynamic simulations. So what you see here is a cluster of 19 strands of this coordination polymer. And then we have 10 extra strands around it, around this cluster made of 19. So what you see there, you see these blue dots. This is the vertex of the hexagon, and then the green is the face. So this is a density map, because what we did is it was to put these 10 strands and to see, let the system, evolve and see which of these 10 strands where they will react first. And what you clearly see in this density map is that they tend to react first from the vertices. And this is in fact what we were observing experimentally. And this is very clear here. So the blue, are the ones that are, seeing faster these strands that are around them. So this allows us to prove that what we were observing experimentally, it was, in accordance with theory. But then what we also did, it was to try to isolate the nucleation, the nuclei in this, crystallization process. So what we observe is that at time zero with the microfluidic device, we could achieve these small particles. so we could isolate them, whereas in bulk it was not possible. So we always had empty TM grids. But here, we were astonished when we observed that. So what you see there is this pathway here that I presented in the mesoscale assembly. So we have the formation of hexagonal particles that they are all self-assembling to generate the final thermodynamic product. So this is a clear example of mesoscale assembly on functional, in this case, a spin crossover compound. So we were lucky enough to also get the cover here. And this is basically the slide that summarizes the work. So what we could see is that with microfluidics, with these controlled reaction diffusion conditions, we could unveil these two crystallization pathways that you cannot observe in bulk synthesis. But what we realize is that in bulk, we have a clear example of the mesoscale assembly with the formation of nanocrystals that then self-assemble to generate the final crystal structure. So now, chemical gradients, why are they useful? So, you know, long time ago, and so when I had to write my Ramon y Cajal research plan long time ago, so I was already thinking about this. I mean, I knew that microfluidics was an ideal technology to control chemical gradients in time and space. So the idea then it was, how can we apply this to materials, material synthesis, or even to crystallization processes? So I have an example for crystallization processes, but I didn't include it here. So if you are interested, afterwards I can show you the results, but I will focus on material synthesis now. So the question that I was, you know, trying to answer is with organic photovoltaics. So as you know, in organic photovoltaics, you have a donor and an acceptor, and you always have to do mixtures of the two. You do multiple mixtures to try to find that mixture that will give you the highest photocurrent. So this is done via this Edisonian approach, right? So you spend a lot of time doing different ratios in order to find the ratio with the highest efficiency. So the idea here would be like, if we are able to generate chemical gradients with one single sample, we will then be able to tell which ratio is the one that gives us the highest efficiency. And this is something that we did together with Mariano Campoy at the MAP. So we, you know, assembled the microfluid device to a blade coater. And what you, because of the laminar flow condition, what you can achieve is a perfect, you know, mixing of two versions. And then with the blade coater, you can have this the formation of this graded film. So in that case, we took very well-known polymers in the field of photovoltaics. And what we then did is basically to flow them through this microfluid device and to generate the film of these two polymers with a control chemical gradient. So this is actually what you can see, the gradient from, you know, the donor to the acceptor. And here you have the ratios where you achieve the highest photocurrent. So this is just one example. We are still working on this idea of controlling chemical gradients in order to achieve, you know, to do material synthesis. But what I would like to highlight and of what I've shown until now is what reaction diffusion conditions have allowed us so far. So what we have shown is that RD conditions can be good, you know, to achieve this pathway complexity, can be good to accelerate crystallization processes, can also be good to somehow, you know, generate morphologies of crystals that are not achievable with conventional turbulent mixing. And then they can also allow us to generate chemical gradients, and we just saw why these chemical gradients can be important. So, and this all has been done only with this dimensionless number, the Reynolds number. So we did all this work just trying to control and to decrease the Reynolds number. Currently in my group, what we are focusing is on a different dimensionless number, the Grashof number. And this is the ratio between the buoyancy forces and the viscous forces. So again, the viscous forces dominate, but here we, avoid convections. What is a buoyancy force? So, okay, this is the problem of having an online webinar. Normally what I do is I ask to people what this is, but I will answer myself now. So this is a chemical garden, okay? So for a long time, people try to understand how these structures are being generated. So what you see here is a movie of how these chemical gardens work. And, the research community was, studying this for a long time because they thought that the original life emerged from this kind of chemistry. So what you have here is a bit the process of explaining how these chemical gardens occur. And what you see is that in this case, you have the formation of this semi-permeable membrane. So this is, growing this semi-permeable membrane, and at some point it breaks. And then due to buoyancy forces, you have the formation of these columns that you see there. And here, you have a differential potential that is large. So, and this is why people thought that this could lead to the origin of life, because it was possible to reduce, for example, CO2 and generate the first amino acids. But all this type of research stopped when Rosalind Franklin, discovered the double helix of DNA. Then the research community started to work on the double helix of DNA, and they stopped with this kind of research. But I have to say that there is now cost action ongoing, and the chair of the action is located in Granada. So it's been hosted here in Spain, and all this research field is called chemobryonics. So what I think is very interesting here is, first, I wanted to show you what are these buoyancy forces. So you can see here the formation of why they are useful. And how they generate is, again, because these structures can generate because you have reaction-diffusion control. You have osmotic, pressures, the step concentration gradients, and the confined spaces. So, but most importantly, I wanted also to highlight here that the first Nobel Prize in chemistry was given to Van Hoff because of this, the osmotic pressure, right? So all the laws that he, discovered based on processes like the one shown here. So, okay, so the question here is, what can we achieve when we have a low Grashof number? Well, if we look at this is a crystal that is growing, we see that we cannot control where the crystal grows, it just grows. We have a polyhedric shape. So, and this is, based on the crystallographic information that this material has. But there are some processes that are ongoing very close to the crystal growth. So there are some depletion zones. There are some convections being generated while the crystal grows. So if we are able to achieve this low Grashof number, some of these processes will be reduced. And the idea here of our research is, what will be the effect of these low Grashof numbers in the growth of crystals, in the crystal growth? So let me just explain briefly a microfluidic device that we developed some years ago. This is a double layer microfluidic device. So what you have is two layers. This is the top one is called the control layer, and this is the fluidic layer. So what you see here, like yellow and blue, these are food dyes, right? And they are in water. So what you see there, this is the upper layer. So this is the control layer. And here, what we are flashing are gases. So what you will see in this video is exactly the process here. So you see, we closed the valves, so, and then we open the middle one. So this is, you see, now it's actuated, now we deactivate it. And what we can achieve here, it's what they describe as a free interface diffusion process. So there are no convections occurring there. Well, when I read these papers a long time ago, the group of Professor Stephen Quake at Stanford University, they were the ones developing this type of microfluidic devices, and they were always talking about this free interface diffusion process. They were using this in order to crystallize proteins or big biomolecules that are difficult to crystallize. So they were, using this approach in order to crystallize them. And to be honest, I was very surprised because during my time at Zurich, I went to Novartis, and they are actually using these kind of devices to crystallize some of the drugs that they are producing. So because, it's as I said, it's a free interface diffusion process what you have there. But we did this video here because I wanted, you see, at the end we have at the middle the green color because yellow and blue generate green, but we could not see, what is really happening in the middle. So I didn't believe that we will have this free interface diffusion process, and this is why then I decided to work with this coordination polymer here. So this imidazole derivative with the zinc. It's known that these two, when they react, they generate a fluorescent coordination polymer. And look what happens. This is the valve, right? This is the valve. And here we have the container with the Biggs and the zinc. So as soon as we open the valve, what we see is that the coordination polymer is generated really, at the interface of the two. And then, of course, because of the diffusion coefficient, so this is, it will move faster, then you have the formation towards the Biggs, container. So what this clearly shows is that, in fact, it's true. I mean, with this kind of approach, it's possible to achieve this free interface diffusion process. So why I'm introducing this? Because under these conditions, we can have this low Grashof number. And this is what we did here now with this coordination, with this metal organic framework. So we have this peptide that when it reacts with copper, we have the formation of this chiral MOF. This was done in collaboration with Carlos Martí Castaldo at the University of Valencia. So what we have is, again, our double layer microfluidic device. So, and what you can see here is how this MOF crystal grows in these confined environments. So we also did a segmentation algorithm that will allow us to follow the growth of the crystal in these microfluidic devices. So then we have this area versus time plots. We did a mathematical model to extract all the constants of the growth, and this is how the fitting of our model looks with the experimental data. So it's very, very accurate. And what we see here is that, of course, we cannot control really when we want the nucleation to happen. This is clearly shown here. So we have a lag time. So all the crystals grow, at different times. But what we observe is that there is a critical concentration. So, and this is 100 millimolar. Above this concentration, what we can have is a constant growth of the crystal. So if we add the solution, this MOF crystal will continue growing. If we are below, then we can dissolve it. So this is the ideal condition then to try to shape the crystal. So and this is something that we try to do with this microfluidic device. So as soon as we add new fresh solution, so it gets the growth, it gets accelerated, and this is what you see there. So with that, what we managed to do is by changing, you know, the chip design, we could achieve single crystals with very integrated morphologies. So you see there, it's also a single crystal. It has this U shape, and then we also did, you know, crystals that in this case they were not single crystal, but if you look at this here, this is a millimeter long. So we could control very nicely not only the length of the single crystal, but also the shape. As you see, normally these crystals have a polyhedral shape, but in that case, you see that they have this semicircle shape. But we can also do flat crystals. So if we change the microfluidic device, what we can grow is like a kind of film with the same chiral morph. So this is what, yeah, it's also a single crystal. So yeah, we were lucky to get here also the cover of the journal. But this is something that we developed later. So we did that with, let's say, a 3D morph. But the idea is that, or the idea we had in this work is, can we extrapolate that to 2D materials? Well, here I just gave some examples of how 2D materials can be achieved. So one of the most used approaches is are these two here, the liquid-liquid interfaces or air-liquid interfaces. But what happens here is that you generate convection as well, because as soon as you start to have, you know, the crystal being generated, you know, the regions will be consumed, and you will have, you know, depletions and the formation of natural convection in this reaction container. So the idea, it was to, you know, achieve a microfluidic device that will allow us to have, you know, a low Grashof number. So as you know, that probably you know, so a place where you also have a low Grashof number, it's at the International Space Station. So there, the Grashof number is very low, and this has proved to be, you know, an ideal condition, for instance, to grow Teflon. So Teflon, it's a glass that it's supposed to have much rich qualities than silicon. So, for instance, for all the optics, and it will be great to have, you know, single crystals of Teflon. But what happens is that under, you know, yeah, on Earth, with the normal gravity that we have on Earth, it's not possible to achieve single crystals with Teflon. We also have, there are many grain boundaries that then, you know, made this material to reduce a lot the good properties that it has. So there are currently many industries and companies in the States trying to, you know, do experiments in this International Space Station to achieve single crystals with these materials, or even to, you know, do 3D cultures, because to generate new tissues. Because what happens if you try to do a 3D culture in conventional gravity conditions on Earth is that once you will add a second or third cell line on top of one, they will all collapse. But this will not happen at the International Space Station. So this is, you know, the approach that we wanted to have here. We wanted to achieve the conditions or simulate the conditions that you will have at the International Space Station. And this is what we started to do. So we started to generate this 2D, it's a very well-known 2D morph that is a conductive one. So this normally is being generated with this, let's call it a droplet approach. So what you have is the precursor on the in a droplet, and then you treat this droplet with papers, and you then generate. In this case, you could generate this to the conductive mode. But what happens, these are numerical simulations, is what you see here. Natural convection will evolve. So you can have the precipitation of some crystals here, they will fall, they will, deplete the reactant, you will generate convection. And then what you see is that the diffusion of the regions, it goes in favor of gravity. And this is what you have in our microfluidic device. So what you see is that the convection, if you see at the units, it's reduced by 10,000 times. And then what it happens is the contrary of what we had here. So here, the diffusion of radiation goes in favor of gravity, whereas here is perpendicular. So it's like you are kind of simulating the microgravity condition that you have in the International Space Station. So what we observe is that under these conditions, then we can achieve very long films, centimeter long films of this 2D conductive mode. So then playing with the chemistry of the surface, we can, have an alignment in favor of the surface, or we can, grow the crystals perpendicular to the surface. So we can control the orientation of this 2D conductive mode on the surface. We also use different surfaces. So we did it in glass, in quartz, in gold. So they all work. But what it was also very interesting in our approach is that now we could do, measurements also through the film. So we could measure in plane and out of plane. And this is just a summary of the different results that have been published with this material. So I would like only to highlight, these are the values that we obtain in this work. And these all values, they are mainly done, under vacuum conditions. I have to highlight here that all the measurements we did were at room temperature and atmospheric pressure. And as you see, we have one of the highest values reported until now. So this is also ambient and is higher than ours. But I would like to highlight here that to achieve this conductivity, they were generating pellets, that they were pressed 1 gigapascal. So they had to apply huge pressures to achieve this value here. Our film has no treatment at all. It's being generated and measured directly. So we have a direct integration of our film on these breathe-out components, on these electrodes. And what is also very interesting is that in C, so in the C axis, so through the film, we have this ratio. It's similar to the one you observe in graphite. So we also, redesigned our microfluidic device and did it in a way that we can, change the surface very rapidly with different ones. So this is what you see there. This is quartz, glass, and then we can also have graphite. And we did, in this case, the synthesis of the same curve I showed in the previous slide. So in that case, what we wanted to prove is that when we do the synthesis of this curve, in the conditions, or in the same conditions like in our microfluidic device, in bulk, what we obtain is these microparticles, microcrystalline particles. But in our microfluidic device, with this low Grashof number, what we can achieve is this perfect film. This is what you see here. We can control the thickness. In this case, it was like 60 nanometers, but it's very impressive. It's completely the morphogenesis. It's totally different from what you obtain in the bulk and what we are observing as a result of our reaction under these low Grashof numbers. So yeah, this is what we suggested as a cover, and I'm happy to share with you that this was accepted now as a front cover of Advanced Materials. So I hope that Soon we will have it online. And here what I have is a video of one of these films. So the nice thing of our approach as well is that we can, isolate them, we generate them in our microfluidic device, and then we can just, transfer them to any surface we want and work with them. So to summarize, I hope that I could convince you that, looking at this Navier-Stokes equation for doing chemistry and for, trying to control self-assembly and crystallization processes, it's a good idea. So I think that not so many people are looking at that, but it's very important to have this control over the diffusion of regimes in order to achieve new functionalities as well. And I would like just to, show an application of what can we do with crystals. So again, the Navier-Stokes equation. There is I recommend this paper. It's very nice from Purcell in 1977. It's called Life at Low Reynolds Number. What he was saying here is that, tiny objects, okay, that, have a time symmetric motion, they cannot have a net displacement. So they have to break symmetry in order to move. And this happens when we have low Reynolds number. So when that viscosity is very high. So, I was also very interested on this for obvious reasons. I mean, it's also low Reynolds numbers. And we then started to, talk about this possibility of finding applications of crystals in micro-robotics with a very good friend of mine, Professor Salvador Pané at ETH Zurich, and Professor Bradley Nelson. So they are very well-recognized group in micro and nano-robotics. And, they developed a structure that could break this symmetry and have motion at the nanoscale. And this is a helix. So Brad Nelson was the pioneer on this area. So they developed this helix. So we wrote a project together with Salvador that was founded via ETH. And the idea was this one here. So we have the helix that the group of Professor Brad Nelson developed some years ago. And what we decided to do here was to equip these helixes with MOF crystals. So we need a microfluidic device that enable us to have two different pHs. So pH 7, where the ZIF crystals will be more or less happy, and a pH of 5, where the ZIF crystals will dissolve. And what we did, it was to encapsulate rhodamine on the ZIF crystals. So what you can see is that, I mean, we added, these micro robots at pH 7, and then we injected 4 of them. So 2, they stayed at pH 7, but 2 of them, we moved them to pH 5. So what you see is that now these 2 that were fluorescent, they lose the fluorescence, whereas the ones that stayed at pH 7, they still keep it. So here is what happens when we brought back the 2 micro robots that were at pH 5. So you see we have the 4 of them. These are entangled now, so they are still fluorescent, but these 2, they lost the cargo. They lost the rhodamine that they were carrying in the porous structure. So this is just to give an example. I mean, this we were quite surprised because it had an impact in the field of micro nano robotics. So it was highlighted at CIEN, and then we also got luckily a cover also with this work in advanced materials. So I'm with that. So I would like to finalize my presentation. I hope that it was not too boring and that I could convince you that reaction diffusion conditions, or to control them, can be key to achieve new functionalities and to control crystallization processes. So thank you for your attention.
Thanks, Josep. I think it was just the opposite of boring. It was a very, very interesting talk with many examples of the huge possibilities that microfluidics have. And after all the good things, I would like to start with the bad things of microfluidics that you just mentioned briefly, is the limitation that you have with solvents. So yes. Can you comment a bit of that?
Yeah, so as I said, I mean, we mainly work with polydimethylsiloxane, so with PDMS devices. And the thing is that PDMS, you know, it swells with many solvents, with mainly also polar solvents. Like you cannot work with solvents that are frequently used in chemistry, like dichloromethane, chloroform, hexane, solvents like that. They make the PDMS swell, and then the microfluidic device breaks. So that's a problem. But as I said, we, together with the group in Freiburg, we can now print microfluidic devices made of glass. So in that case, yeah, you could also work with this type of solvents. To be honest, the research that we have done so far on this is very limited. I mean, we didn't focus yet on working on systems that will need to be generated in hexane, for example, or dichloromethane. So there are
temperature.
So yeah, that's a good point. So actually, we managed to set up a system with a Peltier element that allow us also to control, you know, the temperature. But this is a very good question, because, you know, and you know it perfectly, because this is something that also, if I can say it, I don't like it so much when I get that question, and it's in our work, right? In this work here, in this work here, right? So one of the things that the people frequently ask is, what happens if you change solvent? Or what happens if you change temperature? Well, if you do that, what you will do is you will change the energy landscape. And actually, what we want to, you know, prove here is that keeping the energy landscape the same, only because of these reaction diffusion conditions, we can unveil other pathways. So changing the temperature will bring us, you know, to a different thing. And this is, in fact, something that we are starting to look at as well.
Yeah, but I'm thinking more of systems that require high temperature to form.
Yeah. No, yeah, as I said, yeah, we are, yeah, for instance, for coughs, MOFs, it's known that you have to use, in some cases, you need to use high temperatures. And this is something that we are starting to look at as well. But again, there the heat transfer in microfluidic devices, it's very efficient. So you may not require to have so high temperatures for you know, a product to be generated.
And now that you mentioned coughs, so you know that one of the limitations of coughs as well is to obtain single crystals of coughs. So there are only a few numbers of single crystals of coughs. So what about using the microfluidics in the same way as you use for controlling the growth of MOFs? So instead of using the system, the cough that you have used for your experiments, using one of the few coughs that are known to grow large as single crystals, so you can actually have a huge crystal of that cough.
Yeah, we are working on this. I hope that soon we will be able to show it as well. Yeah, but this is a good idea. It's not that easy, no, but I'm very excited because yeah, like 2 weeks ago, we got some preliminary data that looks quite nice.
Similar to that would be like this, the last system that you showed, the two-dimensional system, the conductive one. So if you could the nickel-based one. So if you could create large crystals of that, you could maybe exfoliate it and then obtain a single layer.
Yeah, this we didn't try. I mean, what we are trying is to control the thickness. I mean, in the case of COFs, that's possible. I showed that we can achieve like 60 nanometers. We can also go less than that and also higher. But in the case of MOFs, things are a bit different. So it's not that easy to control the thickness. I mean, we are still working on this, but for COFs, it seems to be feasible to control the thickness of the films that we generate with our approach, but not for MOFs.
And in the systems, the single crystals of MOFs, what about the mosaicity of the system? Is that very low? So it's truly a single crystal, or it's just something that you examine by the eye? So how do you examine? How can you prove that it's truly a single crystal?
We do Muller matrix. So we have a colleague here at the University of Barcelona, and we are currently running a lot of experiments with him. Because there you can you can see easily if it's a single crystal, if it has the same orientation, if it does not. So this is what we are currently using. But then, you know, our microfluidic devices, they are not easy to produce. But if you know how to do it, it's also possible to disassemble them. So, and once you do so, you can, you know, pick up the crystals and just measure them. So this is, in that case, this is what we did. And currently, as I said, we are using this Muller matrix approach to make these studies.
Because it reminds me a bit about like H tubes and U tubes for crystallization that we normally use in the lab. That at the end, the limitation is when you modify the diffusion and all that, and then you have the single crystal, and the problem is retrieving the single crystal. That from an H tube that is large, is quite, at the end is simple, but maybe it's more
in this case,
microfluidic devices.
In this case, what we can do is just to peel off the PDMS. We peel it off, and then we have the crystals either on the surface or the PDMS surface. So, and then we just have to pick them up. So,
and then coming with this analogy with the U tube or the H tube, we also can modify them in the U tube to have 3 components or even 4 components. So can you also do that with microfluidics instead of having only 2 components, so component A and component B, to have a third component?
This is something that, and I don't know if there is anyone from the microfluidics field here now in the audience, but I mean, you have to consider one thing here, is that everything we wanted to have in all the works we did is to have this controlled reaction diffusion process. As soon as you start to introduce new flows, the conditions, the back pressure, everything will change. So it's not going to be easy to maintain these conditions. I mean, you can do it, yes, you could do it, but I've seen, and even I review papers sometimes, that it's, you know, they don't have this controlled reaction diffusion process because they cannot have it. It's like when you know, plug one chip to another chip and then to another. This is flow chemistry. It's not really microfluidics. This is something, I don't know why you would use this. I mean, you could do it also in, you know, in a beaker in the lab. So because you have turbulent flows. So one has to be very careful when adding new reagents. Also, you can have precipitation. when you work in continuous flow. So if you have, let's say, 3 components, right? It may happen that this in the middle will react with this one here, but also with the one there. So what is going to happen in the microfluid device? You will probably have clogging because you will be generating crystals here and there in the 2 interfaces. So there are things that one has to consider when going into these directions.
Okay, and then one more thing is that you mentioned in the introduction the different dimensionless numbers that are, so you are focusing on Reynolds numbers and the Grashof number. What about the other number? Can we expect in the future to have
yes,
a talk completed with research on all the numbers?
There are a few more I would like to try, but yeah, for now we have enough work with
Okay.
these 2. No, but I mean, the capillary number is another one that most people in microfluids are using. All the people that do droplet microfluidics, they are considering this dimensionless number as well. And there are many papers on and very good groups working on this. So like Professor Andrew De Mello at ETH, Professor David Pites, Harvard. So recently also Professor Chris Abel, he passed away last year. He was very active also in this field. So yeah, I think that that's the idea, let's say.
Okay, we've got one more question, is that if you could imagine any catalytic process using your microfluidics machine to get kinetically controlled products?
Yeah, this is a very good question. In fact, I mean, there are some people working on this also. So I know a big project now ongoing in Switzerland, where Professor Andrew De Mello is involved, and they are looking into this direction. Yeah, this is a very good idea. Yeah, we don't do anything. You know, my knowledge in catalysis is below 0, so we don't do anything
well,
related to
maybe
that.
in the future you could move slightly there and could find some people interested in this community that may work try your setups for this.
Yeah, no, yeah, that will be nice. Also, I'm also very keen to always learn new things. No, and that will be nice. Yes.
Mm-hmm. Okay. Well, Josep, let me finish just by thanking you again for the
thank you.
talk. And just to everyone, we'll be back with this seminar series after the summer. I don't know, Pilar, if you want to say some final words, please activate the microphone and just say the official goodbye of the season. It seems that she's having problems activating the microphone. So if not, well, I'll be the speaker of her words, as thanking everyone, thanking all the attendees of the 4 seminars that we've had. So this has been the first year that we've organized this type of seminars, and I think they have been very, very successful. We'll continue with them after the summer. So happy summer to all of you, and we'll see you back then. Okay. Bye-bye.
Okay. Thank you very much.
Thank you. Thank you for inviting.
Yeah.
More than welcome.
I don't know.
Bye.
Hello.
Muy bien.